Welcome back to Programming Fluency. This is section 11.4, Defensive Programming. So far you have learned to hunt down bugs after they break your program. In this video you learn the proactive counterpart. You write code that catches mistakes the moment they happen. The best bug is the one you never have to debug. Let's begin. So far you have learned reactive skills. You write code, something breaks, and you hunt for the cause with GDB and Valgrind. In this video you learn the proactive counterpart, defensive programming. You write code that catches mistakes at the moment they happen, before they can spread into a mysterious failure somewhere else. The best bug is the one you never have to debug. Let's get started. This is the plan for this video. First, the assert macro, a checkpoint that fails fast on a broken assumption. Next, preconditions and postconditions, a contract between a function and its callers. Then disabling assertions within debug, how to turn them off in release, and why side effects are banned. After that, safe string functions, snprintf and strncpy as guardrails. Finally, a layered defense, warnings, assertions, safe functions, and runtime tools together. Let's start with the assert macro. It is declared in assert.h, and it takes a single expression. If the expression is true, nothing happens and execution continues. If it is false, assert prints a diagnostic and terminates the program immediately. This divide function asserts that b is not equal to 0.0 before dividing. If you call divide with a 0 denominator, the assertion fires. It prints the file name, the line number, the function name, and the failed expression, b not equal to 0.0. Then it calls abort. The message ends with core dumped, which just means the operating system saved a memory snapshot for debugging, and you can ignore that part for now. An assertion failure means a programming error, and crashing right at the source is better than continuing with corrupted data. This figure shows the checkpoint behavior. A function is called and reaches the assertion, which checks a condition. If the condition is true, execution continues normally down the green path. If it is false, it takes the red path, prints a diagnostic with the file, line, and expression, and calls abort. The key principle is fail fast. Stop at the exact point of error, not hours later when corrupted data causes a mysterious crash somewhere else. So assert evaluates an expression at runtime. If true, continue. If false, print the file, line, function, and expression, then abort. Use assertions for conditions that must always be true if your code is correct. Assertions are most valuable when they express a contract between a function and its callers. Look at stack push. It has two preconditions. The stack must not be null and the stack must not be full. Then it does the work. Then two postconditions. The size grew and the top element is the value we just pushed. Preconditions are the caller's responsibility. Postconditions are the functions. Without the full stack check, push would write past the end of the data array, a silent buffer overflow that corrupts memory and crashes much later. Let's define both halves of the contract precisely. A precondition is a condition that must be true when a function is called. It is the caller's responsibility, and you verify it with assert at the start. For example, assert size greater than 0 at the top of a function that computes an average. A postcondition is a condition that must be true when a function returns. It is the function's responsibility, verified with assert before returning. For example, assert result greater than or equal to 0 before returning a value that should always be non-negative. One subtlety. An assert of s not equal to null right after malloc is neither a precondition nor a postcondition. It is a resource check, and in production code, allocation failure is a runtime error, not a bug, so use real error handling. If s is null, return null. Assertions have a small runtime cost because each one evaluates an expression. For production builds where performance matters, you can disable all assertions by defining the ndebug macro, usually with the flag -big D ndebug. When ndebug is defined, the preprocessor expands every assertive expression to void zero, literally nothing. The expression is never evaluated. So the typical workflow uses two build configurations. A debug build with -G-big O0 keeps assertions enabled to catch bugs during development. A release build with -big D ndebug-big O2 disables them for maximum performance in production. Assertions protect you exactly when you are writing and testing code, and step aside in production, where real error handling takes over. This is the most important rule about assertions. Never put side effects inside assert. Look at these two examples. Assert of I++ less than 10 and assert of red record equals 0. In a debug build they work, but when ndebug is defined, the entire expression disappears, including the I++ and the function call. So I is never incremented and red record is never called. The fix is to separate the action from the check. Call red record first, store the result in a variable, and then assert on that variable. Now the function always runs, and only the check is removed by ndebug. Buffer overflows often come from an unbounded string function, one that writes as many bytes as needed without checking the destination size. C's standard library has two generations of these functions. strcpy becomes strncpy, which copies at most n bytes. strc a t becomes strnc a t, which appends at most n bytes. sprintf becomes snprintf, which writes at most n bytes, including the terminator. And gets becomes fgets, which reads at most n-1 bytes. Each safe version takes a maximum size argument, but it is only safe when that size is the destination's actual remaining capacity. Pass too large a count, and strncpy or strnc a t can still overflow. For strnc a t, the limit is capacity minus the current length minus 1. Used with the right size, these consistently eliminate the most common class of buffer overflows. This is why snprintf is the single most useful safe string function. Look at greetSafe. It uses one snprintf call to build the whole greeting. snprintf writes at most size of greeting bytes, including the null terminator. If the formatted string would be longer, it truncates. The output is cut short, but the buffer is never overflowed. And snprintf returns the number of characters that would have been written, so if that is greater than or equal to the buffer size, you know truncation happened and can report it. For a short name, it prints in full. For a long name, it prints truncated safely. Individual techniques protect individual operations. Coding standards protect the whole code base by making dangerous patterns structurally unlikely. A coding standard is a set of rules every function follows. This is a practical checklist. Rule 1. Initialize every variable at declaration, like int count equals 0. This eliminates the entire class of uninitialized variable bugs. Rule 2. Check every pointer before dereferencing it. Rule 3. Use bounded string functions only, snprintf, strncpy, and fgets. Rule 4, use size of on the buffer, not the pointer, and when the buffer is a pointer, track its size in a separate variable. Rule 5, compile with maximum warnings, -w all, -w extra, -w pedantic, and -w error, which turns every warning into an error you must fix. The practices in this section form a layered defense, shown in this figure. Each layer catches bugs that slip past the one above it. Layer 1, compiler warnings, catch uninitialized variables, type mismatches, and missing return values at compile time. Layer 2, assertions, catch logic errors, the violated contracts during testing. Layer 3, safe functions, prevent buffer overflows structurally, because the dangerous operation simply cannot happen. Layer 4, runtime tools like Valgrind and address sanitizer, catch the memory errors that survive the first 3 layers. No single layer catches everything, but together they cover nearly every category of C bug. 2 common mistakes to close out. First, using assert for error handling. If you write assert of fopen not equal to null, then under ndebug the whole thing vanishes, including the fopen call, so the file is never opened. And a missing file is a runtime error, not a programming bug. The fix is real error handling. Call fopen, and if it returns null, print an error in return. Second, using size of the pointer instead of the buffer size. If buff is a char pointer and you write strncpy of buff, source size of buff, then size of buff is the pointer size, 8 bytes on a 64-bit system, not the buffer size. You copy at most 8 bytes. The fix is to track the buffer size in a variable and use that. Size of only gives the buffer size for stack arrays, never for pointers. Let's recap. Debugging is reactive. You write code, something breaks, and you investigate. Defensive programming is proactive. You write code that catches mistakes the moment they happen. Use assert for conditions that must always be true if your code is correct. It aborts with a diagnostic naming the file, line, and expression. Write preconditions and postconditions as a functions contract. Disable assertions in release builds with ndebug, and never put side effects inside assert. Replace unsafe string functions with bounded ones, snprintf, strncpy, and fgets. And layer your defenses. Compiler warnings, assertions, safe functions, and runtime tools together. Next, you have learned C one concept at a time, ending with debugging. In the final chapter, you will assemble every skill into one project, a complete command line utility, from specification all the way to working software.